The great thing about PIV, because it's not limited to any size. You can do it at any scale, right? From like kilometer scale, if you want to track clouds, for example. But you can also, of course, do it for the flow inside cells, or the flow out around cells.
Join the conversation with William, the developer of PIVLab, as he shares insights into the world of particle image velocimetry, PIV, and its application. Discover how PIV accurately measures fluid velocity non-invasively, revolutionizing research across industries. Delve into the development journey of PIVLab, including collaborations, key features, and future advancements for aerodynamic studies. Explore the advanced hardware setups, camera technologies, and educational prospects offered by PIVLab for enhanced fluid velocity measurements. Welcome to Inspiring Computing. This podcast is where computing meets the real world. Inspiring Computing aims to trigger your curiosity by talking to proficient and advanced MATLAB, Python, and Julia users who use these tools to deepen their understanding of the world around them by simulating it, exploring trade-offs, and gaining insights that help their companies add more value. In addition to proficient users, we will be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives their development and what issues they're solving for others to benefit from. Welcome, William, to Inspiring Computing.
Thanks a lot. Hi.
You are a famous person in the MathWorks world or the MATLAB ecosystem because you're the author of something called PIVLab, which is one of the most popular community toolboxes. And you are here today because I'm super curious about it. But before we go into what exactly is PIV and particle image velocimetry, I would like to understand, how does someone like yourself end up developing this? So can you maybe give me your superhero origin story?
Yes, of course. It all started with some research that I've done in a lab in Groningen in the Netherlands, together with my doctoral father. When he was a researcher, he still is a researcher, but when he was younger, he already programmed his own PIV software. And that was also running nicely, but it could only process single images. And I was doing a research project where I had to process like tons of images and also take images from several perspectives and put them together and have everything time resolved. So it was a lot of image data that I had to process, and the only software that I had was a software that could process single images. So this was already a hard start. I first experimented with some macros in Windows or stuff like that, so that a mouse clicks the program and takes images and stuff like that. Yeah, but that didn't work out nicely. And then another student came to me and was talking to me about something like Excel on steroids, or however you would pronounce that, as a better Excel. And that was, at that time, it was MATLAB. And then I got interested in MATLAB, and I said to myself that it would be a good idea to make your own PIV software that can process tons of data. That was the original idea.
So maybe just to take a step back, so when you say PIV, for the listeners who don't know what it is, can you describe what is PIV and what problem does it actually solve?
Yeah, it is actually a very simple technique, and there's some math involved in it. That's true, and there are a lot of steps and some hardware also involved in it. But in the end, it's very simple, because what PIV does, that is something that your brain and your eyes can also do. So first of all, what you want to do with PIV, particle image velocimetry, is that you want to measure velocities in fluids. And you can, of course, use all kinds of measurement devices, anemometers, that you just put into your flow, and then you can measure how fast the flow goes by. But in that case, you will always disturb your flow, right? You will always be in contact with your flow, and it's not always possible to just open a hole in your wind tunnel or whatever, or in your engine, and then stick something inside and measure the velocities, right? And you will also, with these devices, will only get a single point measurement, so only at a single point. So, for example, hot wire anemometers, these are popular measurement devices that you can stick into some fluid or some air, something, and then you measure the velocities. And PIV is a bit different, because PIV works by illuminating a thin sheet inside your fluid. And before you can illuminate that, you put some particles inside your fluid. So it can be like very small droplets that you put into air, for example, or it can be small, like 50 micron large plastic particles or glass particles that you put into your water, for example. And then you need some illumination source, and you generate a light sheet, a thin light sheet. You illuminate these particles in your fluid, and then you just put a camera perpendicular to that light sheet and film these particles, the motion of the particles. And that already at that step, your eyes can already see all the motion. You could take some pictures and then just measure by hand the displacement of the particles from one image to the other. And in the end, this is already PIV. But of course, this would be quite a lot of work to do this for all the particles. And that is why, some software, for example, PIVLab comes into play, and it does this particle tracking automatically. So this is the idea of PIV.
So when you say particle tracking, right? Why would anyone want to do this? So you said this was for your research. So I'm assuming this is broader than just research, right? So can you maybe give me an example where somebody benefits from doing this and uses it?
Yeah, it's of course used a lot in research, right? If you want to develop new devices, you want to know how the flow goes around it. But this is also the main application, research. If you want to understand how flows flow around bodies or inside bodies, and you want to optimize the geometry of the bodies, for example, to save energy or to make things faster. We've done measurements in turbochargers of large engines where they just want to know the velocities inside the engine. And there's no other way of determining the velocities also in a two-dimensional plane, right? It's not only a single point that you measure with PIV, but you can measure a whole light sheet, a whole plane, and also time resolved, of course. Yeah, and if you want to know how your turbocharger works and how also your CFD simulations, so your computational fluid dynamics simulations, if you want to tweak them, actually that's what most of the time people do. Or it's my impression. I'm not a CFD guy, so maybe some people might feel offended, but for me it sometimes seems they're doing some CFD with the newest technology that they have, the largest computers, and then they see some output, and then they want to know if this output actually is true, and then they come to the experimental guys that do PIV of the same model and the same situation, and then the CFD guys tweak their simulations to match the experimental results, right? That is, I think it's fine. This is the way how it goes. And I think this is the way how it should go, because sometimes you see some CFD simulations where people just simulate something, but it can be anything can come out, right? It's not, I wouldn't, if you don't do this direct numerical simulation, which takes ages or is even impossible at higher Reynolds numbers, I think then you have to always validate your CFD simulations with some reality.
So maybe to make sure I understand, so when you say CFD, so this is research or someone saying, well, given that it's so difficult to set up a hardware setup, maybe I should start off by simulating it, and then they take shortcuts along the way, saying maybe this is a symmetrical object, so therefore I'll simulate half of it, and then the other half has to be equal, and maybe you ignore the interferences, and then there's shortcuts here and there, which slowly but surely deviate from the absolute truth. And maybe for certain applications that's okay. But if I understand correctly, PIVLab is a software that powered by MATLAB that kind of enables people to ground those assessments.
Yeah, exactly. And also doing some experimental work is also very time consuming and can also be very expensive. For example, if you want to test several shapes, right? Several, I don't know, spoilers of the rear spoilers of a car or something like this. It would be very expensive to manufacture all of these, test all of these, get the measurement time in the wind tunnel. It's super expensive. And for these cases, I think simulations they always make perfect sense. But in this case, they, again, make a lot more sense, because you just simulate one device, you validate this one device, and then all the modifications, you can do them in the computer only in the simulation. And then you can test whole ranges of setups. So sense, yes.
So when I was doing a bit of research for the PIV, I always thought it was more for wind turbines as an alternative. But then I seem to understand from you that it's not only for air, but also maybe for fluid, and maybe fluid dynamics is a stronger area for this. But does this only apply to large scale things, or are we talking about tiny little things? Is this something that we use on microscopes and see biology and moving cells, or is this something that I should have a mental image that this is really only for large devices or reasonably large devices? Talk me through how big or small things can get when you're using PIV.
Yeah, that is the great thing about PIV, because it's not limited to any size. You can do it at any scale, right? From like kilometer scale, if you want to track clouds, for example, you can do this. But you can also, of course, do it for the flow inside cells, or the flow out around cells, or all kinds of organisms. I myself, I'm a biologist by training. So I've done a lot of research also around animals, so like around birds or fish. And I know from the user community of PIVLab that there are really a lot of people that use this technique for tracking the motion of cells and stuff like this. Or also, there are the really diverse applications.
So to double click on something you said there. So you said you're a biologist. So how does a biologist who inherently not study computer science and focus on biology come to a place of building one of the most popular software packages around PIV? Can you maybe tell me how you went from this journey of, I like the biology, and then now you're working in a company that focuses on empowering other people to leverage PIV? Tell me a little bit more about that journey.
Yeah, it's indeed a little bit of a strange journey, but I think that's how life goes, right? Yeah, because initially I always wanted to study something with like technology or engineering or something like this. But I also felt that because this is a very strong interest of mine, technology and stuff like this. So I thought that, this is fine if I do this, but I also want to learn the other side of the world and learn something more about biology. And there's this discipline called biomimetics that also focuses on how animals move, how they generate thrust or lift, or how they save energy. And this is, of course, also has to do a lot of things to do with engineering, but it's also based on biological principles like evolution and stuff like this. So this actually fits nicely together. And that's why I decided that I would maybe start first with biology and then later on move a little bit to the biomechanics side. And that's also what I did. And when I say I'm interested in technology, I was always interested, or since quite a long time, in microcontrollers, in programming microcontrollers, because I think it's super amazing that you can do everything that you want to do, automate everything that you can imagine if you're able to program microcontrollers. And also I was always interested in model airplanes, designing model airplanes, stuff like this. So aerodynamics was also something that I really enjoyed, and then I started combining like aerodynamics or mechanical design and programming by building some drones. So I think some of the first open source drones that were available are actually also from me. So I have been famous for this in the past. Now I'm not famous anymore for this anymore, because there's DJI, like a huge drone manufacturer, and they rule the world, and they do it. They have absolutely awesome technology. So it's fine that they rule the world, I think. But I've done a lot of technology related things in the past too. And it has become a little bit less now because I have so many other things to do in my life. And also family plays an important role, of course. But that's why I'm so happy that I can now today work on PIV software or on programming during my work time. It's not a hobby anymore. I can do it during my work time, and that's absolutely perfect to develop stuff and to also have some time for it.
Just to be clear, so the PIVLab, this is an open source MATLAB community toolbox that is free for everybody in the world to use. But you developed it as a hobby, but now, if I understand correctly, in your current company, Optolution, you leverage it. So maybe can you tell me a little bit more about what does Optolution actually do?
Yeah, I joined Optolution, I think, about 5 years ago. And they were always doing laser optical flow measurement technology. So something else that is called laser Doppler velocimetry. That is another technology that uses lasers to measure velocities in fluids. They did a lot of this stuff. And then I joined the company because they also wanted to broaden a bit. They also wanted to do more stuff that is related to laser optical flow measurements. And that's when I joined. And I brought PIVLab to the company. And in the beginning, it is still an open source software where we don't get any money for. But we thought about what can we actually do to support the development of PIVLab during my work time, and how can we maybe if it's still open source, how can we make some money with it by giving support? That was the first idea. We give some extra supports that is paid, for example, premium support. And then later on, I got the idea that it would be a good idea just to develop hardware for this, right? Because PIV, as I explained, you can use it with all kinds of images, like images from cells and stuff like this, or images from sand and gravel that is moving because a wheel is turning on top of it. That can always be done without any hardware, just by using PIVLab to process the images. But if you want to do proper analysis of flow velocities, then you actually need a good illumination source. And in this case, it's, I would say, always a laser, and you need a good camera, and everything needs to be synchronized. So the idea was if we bring lasers and cameras and synchronization technology to PIVLab, then we can sell this hardware. No one has to buy it, right? Because the rest is still free. But if you want to use our hardware, then you can use the free software PIVLab. It controls our hardware, and then you can do, for relatively low cost, you can do pretty nice PIV experiments in fluids.
So if I understand correctly, the software is a necessity, so you don't need to have your own hardware. So you could take a microscope and you take every few seconds, you take a few pictures or nanoseconds or whatever your time range is, and then you give a series of images to PIVLab. But I think what you're saying is actually the real benefit to really do this, there's a whole hardware rig needed. So can you maybe give me a bit more specifications of what type of hardware? I think you called out a key thing there of synchronizing everything. Can you walk me through what do you mean by synchronizing everything, and why is that so important?
Yeah, one of the main tasks when we started to make some hardware for PIVLab and also to write the software inside PIVLab to control the hardware, one of the main tasks was to make everything as simple as possible, right? As cheap as possible. That was also a goal, because other companies can do awesome hardware, but that costs a lot of money, and we sort of can't compete with them because we're a very small company of only 4 people. So our focus is a lower cost equipment. And then we decided to make everything as simple as possible in PIVLab. And what you need is a illumination source to get this illuminated plane inside your fluid. You need a camera that films perpendicular to this illuminated source. And then we are not using a continuous illumination, but we are using a pulsed illumination. So we are only flashing the laser. And the idea behind this is that if we do, we can get a very small time delay between 2 laser pulses by using regular or almost regular cameras. If we, for example, take a camera that has 10 hertz, right? It captures at 10 hertz. This would mean that if you're using continuous illumination, this would mean that if you go from one image to the other, your time spacing between these 2 images would be like 0.1 seconds, right? Like 1 divided by 10 hertz. So this would mean if you have such a long delay, 0.1 seconds is pretty long, such a long delay from one image to the other, then your flow must only move very slowly, because otherwise you cannot do PIV. If it displaces too many pixels from one image to the other, then you cannot find particles back and do your processing on it. So the idea is that if you do pulse illumination, you can do one of these light pulses at the very end of the first image that you capture, and the next light pulse comes at the very beginning of the subsequent image. And in this case, you have the temporal spacing between these 2 laser pulses and these 2 images is very short, and you can use like a 10 hertz camera to capture very high flow velocities. And that is why you need a synchronizer. And also, it's not always possible to adjust the frame rate of a camera like you wish, right? And this pulse spacing, we can adjust it as we wish. We can also make the pulses longer or shorter if we need more light and stuff like this. So this is really, one of the hard or most important parts inside PIV, I would say. And it's called, if you want to Google it, the name is called frame straddling. So it's a technique that is known before, right? But we have just employed it and used it for our system too, of course.
Right, because I'm assuming to get this working correctly, it's not so easy, right? So how do you actually test it? So if you set up a hardware rig and you say, okay, now it's working, but how do you know if it really is working and if your synchronization is perfect? Do you have a way of testing this, or is this just experience that kicks in?
No, of course we have to test. that's one of my main duties, that I'm testing everything. Maybe sometimes testing too often. But yeah, it's true. It's good that you asked this question, because it's actually a very difficult thing. If you are measuring velocities in fluids, you never know the ground truth, right? Because you don't have any other reference. In many cases, it's not possible to compare it to some other measurement technique. So this is very difficult. For the algorithms, you would use synthetic images to test that your algorithms are working, because then you know exactly what displacements you have in your synthetic data, and then you can process it. But it's true that for developing synchronizers and stuff like that, it's difficult to test it. Of course, we could just check the pulse generation by using some oscilloscopes. We have some very nice many oscilloscopes with many channels at work, of course, to test this. But one method also to test the whole system is to use I don't know how you call it. It's where you put these LPs on it, like, how is it? In German, it's Schallplatte. I don't know if you have any idea what this means. Vinyl discs. And these devices, they are built to rotate at a very constant velocity, right?
Yeah.
Because otherwise you would hear that the sound is changing and it was in the air, but they are built to really turn at a constant rate. And you can just print some particle patterns on paper, glue that on these disc players, and then you can put your camera on top of it and record that. And then you can, again, use pulse illumination, stuff like that. And then you can really measure displacements very accurately with a real camera and a real synchronization unit.
I see. So that's a way of calibrating to make sure that everything, your setup is correct. And I guess this is an interesting technique that you're calling out. But I'm curious so if I understand correctly, so you developed the software, you decide, and you chose MATLAB, and we'll get into that in a second of why you chose MATLAB. But then the insights that you get is from a well set up, calibrated, working setup. But does this last forever, or do you go in and help people set this up? Does it suffer from a bias? Are there steps that people need to run before they do their experiments? So I'm thinking in the back of my mind, like if you want to measure fluid flow, you don't do it just once. Maybe you do it 10 times and you take the average of all 10 times. And how do you know if your setup is slowly but surely introducing a delay or a bias of some sort? How do you check that? Or is it the common workflow? You say you do it once and okay, that's the experiment, let's run with it.
Yeah, there are many things that could change. If you're doing an experiment in a wind tunnel, for example, right? Then there are many things that could change, and you would, to have statistically significant results. Ideally, that's what I learned in university, you would take all your experimental stuff out of the wind tunnel and then put it back in again. So you make it unrelated to previous errors, right? Put it in again and do the whole experiment again. And then you check if there's any difference. And you do that many times. That would be what you ideally would do, right? Because the flow velocities inside the wind tunnel, they could change. The model could have moved. There are many things that could go wrong. And this is, of course, always a problem of the experimenter. This is not something that we can give hints how to solve these problems. But of course, for PIV, you also have to do a calibration. That's, of course, always needs to be done. Your conversion factor from pixels to meters, for example. So you have to stick in some calibration plate inside your flow. That is sometimes a problem because if you're working in a water tunnel that is completely closed, then you cannot put any calibration target inside your water tunnel, right? But there are some tricks to how you can avoid this and stuff like this. But I think this goes maybe too much into detail of fluid or PIV experiments, yeah.
Right. So I think I'm very excited that you're doing this, and I'm glad that you can do this and help others. But then you developed this in MATLAB, right? I saw that you released a new version, so 3.0. So congratulations on the major release of the new version of PIVLab. But why did you actually choose MATLAB? So you mentioned that someone said, okay, Excel on steroids, and it got you thinking. But you've been using this for quite a few years now. This is not like a 2-month-year-old project. You've been doing this for a series of years. And walk me through your decision process on MATLAB, and also why you stuck to it and what you like about it.
The first idea was really that I needed something that is more performant than Excel. And at that time, that's the very good strategy of MathWorks, just to give MATLAB to every university for not much money, I guess. And also give licenses to the students for very cheap licenses to students. So that is a very good strategy. And that is also how I started with it, right? If it wouldn't be available at the lab at that time, then I would not have started with it. So that's a good decision by MathWorks, of course. And then I just started with it because I I mean, I already told you that I have to process a lot of images, and I also have to do a lot of post-processing on the data that I get, on the velocity maps that I get. I have to combine them in 3 dimensions and stuff like this. And at that time, I couldn't imagine that any other software would be capable of it. I didn't know any other software also. And it was just a nice working environment. It's just like you have this whole user interface of MATLAB where you can see matrices, where you can, with one click, you can visualize matrices and make images from it and look at them. And that's super important, especially for PIV, because you're doing image processing all the time. And if I test 2 different algorithms for pre-processing an image, for example, for enhancing the contrast or something like this, then if I plot the data, my eye can just judge if it's better or worse than before, right? In many cases, this works and gives good results if you do it like this, just looking at your data and then doing some processing and deciding if it's better or not. And that's why MATLAB was suitable for this kind of task. And then, a little bit later, I think 2 years, I was working with PIVLab on my own and also had a different name at that time. And then I started to publish it. And I think another advantage of MathWorks or MATLAB is that you have this file exchange in the internet, right? Where you can upload scripts and everything, and people just find it. If they Google for PIV, for example, and MATLAB, they will directly find the file exchange website. They can, with one click, they can directly download it. And even today, you can just click it once on this website and it will pop up on MATLAB Online, and then everything will run on its own. So it's very comfortable. And I also noticed that there are many people that are using MATLAB. They are searching for software where they can do PIV. So that's what I see in my Google search profiles or whatever. I can see that people search for this. And there are also other projects that do PIV that are open source and that do PIV. For example, OpenPIV is a very nice toolbox. It's based in Python. But there are many more users that use PIVLab than people that use Python, that use OpenPIV. And I'm not sure about the reason why this is the case. Maybe because also OpenPIV it's not that easy. You don't have one single file where you know what to do, and then you click it and then a graphical user interface opens, and then you know what to do, right? In Python, you have to install stuff. There is a graphical user interface as far as I know, but it's not instantly there, right? You have to take some more time to get it running. And I think in MATLAB, it's just way easier. And that's also why I decided to stick to MATLAB. I think it's just an awesome environment. There are many people that use it, and that's the salary for an open source developer, right? If people use your stuff, then that's what you get for it. So that's why I'm still very happy with the choice that I started in MATLAB.
So to double click a little things there. So you said about the user interface. Just as a mental model, when I download and install PIVLab, the first thing I get is it's a toolbox, right? So is it a collection of mathematical functions, or is it more of a user interface where you can click, configure? And when you say click and configure, can you maybe walk me through some of the things of what is the experience like for a first-time user of PIVLab?
Yeah, actually, it's not 100% clear also to me if it's a toolbox or a collection of functions. It's both, but it is bundled in a single file, which is called a toolbox executable, something like this. And the nice thing is that if you have MATLAB, that's of course something that you have to have. You just double click this and it will automatically install like the toolbox, which is a set of functions that you can also use like from the command line. But it also installs, and that is the heart of PIVLab, it also installs something that's called an app or a computer graphical user interface tool. And that is the most important part. And that is automatically installed in MATLAB. It's somewhere on the top. There's a little icon then, and it's super easy to get this started, right? You just click it, it starts, the graphical user interface is there, and then you already know where to click because it says import images and stuff like that. And then you're already done. And all the default settings are chosen so that they work for, I would say, 99% of the image data that you load. The default settings are fine. You can tweak them, of course, a little bit. But every user will get, I think, I measured it once. I think you have to click 5 or 7 times, and then you already have your PIV results. I think the user base is a little bit different between the people that use other open source PIV tools and the people that use PIVLab. Because PIVLab is so simple, there are a lot of video tutorials also. There are a lot of questions from people that never worked with MATLAB before, and they started using MATLAB by using PIVLab. And then sometimes it's a little bit difficult to explain to them how MATLAB works, right? What a variable is and stuff like this. So they have no clue about anything that is related to programming, because probably they just started their studies and stuff like this. So it's all fine. This is not a problem, but it, of course, generates a lot of support, I would say. And people that use other PIV tools like OpenPIV, I think they are much more, they know how to program, they know how to install the environments of Python and stuff like that. I think also they contribute a lot more to OpenPIV. There are a lot more contributors on GitHub, for example. With my tool, there's hardly anyone contributing to it. There are many users, but not many people that help me improving the code.
Right.
So it's a little bit of a pity.
So maybe to dive in a little bit more about how you developed and some of the components in it. So you mentioned the heart of PIVLab is the app. So is this app something that you developed with App Designer, or is this something that you use Java or some other technology? Can you maybe describe a bit of the tech stack behind PIVLab within the MathWorks ecosystem?
Yeah, I first started to develop the graphical user interface using the built-in user interface design. I think it was called Guide, graphical UIDE, whatever. And that was working fine in the very beginning. But my user interface become relatively complex because I have like tons of user interface elements. I think it's 700 buttons, drop downs, stuff like this. So it's quite a lot of stuff. And in the beginning, it was working fine with the built-in user interface editor. But then more people were complaining that the rendering of the graphics doesn't look good on Macintosh or on Apple computers, and it doesn't look good on Linux computers. And it was, because I don't have access to any of these computers, I only have a Windows computer at home. It was impossible for me to debug this. And it was also getting more and more complicated because, things broke in the user interface editor. And that was, getting a lot of extra time that I had to spend with this. And that's when one day I decided to reprogram everything from scratch. So everything is now just coded in a MATLAB M file, because at that time also the app designer was not yet available. So I think I took 2 weeks. That was also when I moved to a new place. My family was still in my old place and I was working for Optolution, first testing if I liked the job. The family moved back later on. Moved with me later on. And that time I had a lot of time in the nights and in the evenings because no family was around. So that's when I decided that I can now really do some hardcore reprogramming, redoing everything. I had to print a lot of papers just with all the graphical user elements printed out so I remember which one is which one. And so I redid everything, which took quite some time. But then, of course, the really big benefit is that it now runs on every computer, and also it runs in the web browser of MATLAB, so that also works nicely. But it was quite some work to get this done.
So just to be clear, so you started with a guide, then App Designer came along, but you're not effectively using App Designer per se. You're writing it as an M file, but you're still using the new widgets components that App Designer supports. So I'm assuming you're using the UI figures, axes, tables, and things like that.
No, actually, I'm not using any features from App Designer yet. I'm thinking about this, but I'm not using any of these. Everything is just coded by hand.
Maybe the other idea is you can also control hardware, right? So you mentioned earlier on the synchronization. So you're using MATLAB to also control hardware setup, but is this specific to the one hardware setup you have? Or do you also enable other end users to use their own hardware, synchronize if they've got different setups? How does that actually work?
Of course, this is a decision that we took, that PIVLab only supports the hardware that we develop at Optolution. But this is also, of course, we also want to sell all devices. That's clear. But it would also be super difficult if I would start to support the hardware from other manufacturers that I don't have in my lab, right? I debugging this, I think that would be a nightmare, right? So everything that is supported by PIVLab, we have it in our lab. I have a bunch of cameras. We decided to go with, I think, 5 different camera types that we like, that we also sell, that people can, of course, also buy from other people. But if they buy it from us, they get more support for it and stuff like this. So the cameras are interfaced by PIVLab by using the image acquisition toolbox. So you need the image acquisition toolbox. So that is really taking off 99% of the development work. By using this toolbox, everything becomes much, much easier. And then we control our hardware, the synchronizer. We control this one, the synchronizer and the laser. We control it by the serial port. So we just have a little serial port connection, and all the commands are sent through the serial port. That is also supported in MATLAB since 2019b, I think. It's incorporated in MATLAB. And that also works nicely, and it works in all cases, right? Everyone has a USB port. We can plug in a converter, and then we use the serial port. That's really nice.
Earlier, you mentioned that in the latest release, you enabled MATLAB Online, right? So this is a possibility for someone to use MATLAB without having to install it on his or her desktop. But can you maybe explain to me how or why would you do that, given that you articulated your cameras seem to be ranging from high-end, medium-end, and maybe low-end? Why did you enable the MATLAB Online in the first place, William?
We enable MATLAB Online, or we put some efforts into making this 100% compatible with MATLAB Online, because we are also selling flow tunnels for educational purposes. So we have a bundle of a flow tunnel with a motor inside it that circulates the water. You can put in some wings into this flow tunnel. Here we have a laser that is put on top of the flow tunnel and one of our lower end cameras. And then this enables you to do PIV experiments in water, the flow around a wing, for example, directly on your desk. So this is super cool for students at universities that can do, a whole PIV setup and experiment with, very easily. And then if they captured the data, they can take the image data that they captured, put it on a USB stick, take it home and do all the processing on their computer or even on their tablet if they don't have a computer, and use MATLAB Online for this, and without a license, right? So this is really super handy, I think, for students.
Wow, that's very impressive. And how big is this setup? Is this kind of like a 1 meter by 1 meter, or is this something that fits easily on a desk?
Yeah, it is 1 meter, but my desk is also 1 meter. So it is 1 meter by, I think, 15 centimeters times 20 centimeters. So it's relatively small. It's like a Prandtl water tunnel, the first water tunnel that was developed by the guy Prandtl, who did a lot of aerodynamic research and a lot of new insights that he got. And his first water tunnel, the principle, how he built it, that's also how we built our water tunnel.
So then the idea is you have an easy entry point for students. And then as they peel away the layers of the onion, so to say, they start to move into research. And then that's where you start saying, okay, I need a more professional hardware setup. And instead of me building it on my own, given that maybe I'm a biologist and my heart is understanding things, but not building hardware setups, that you could facilitate that path with your offering, right?
Yes, exactly. We are trying to also to make our hardware popular. We're trying to have lower cost devices for students and stuff like that, how all companies make it, right?
So then just as an additional thing is, so you mentioned camera. So up until now, I think you've always mentioned that there's one camera. But you said you have 5 cameras in your lab. Is this something that you can use multiple cameras at the same time to measure more than one plane?
Currently, it's just one camera at a time. So we're only doing planar PIV. So in one plane, we have 2 velocity components. But I am thinking since quite a while now about incorporating stereo PIV also in PIVLab. That means that you use 2 cameras, focus on the same sheet, on the same laser sheet. And then by using image camera calibration and stuff like that, you can derive 3 velocity components inside that plane. But this will involve, quite a number of changes in the graphical user interface, also in how you interface the hardware, and also, of course, in all the math that is involved. But I'm in the lucky situation that MathWorks decided to start some support programs for popular MATLAB toolboxes. And I already had 2 projects together with them where they supported the development of PIVLab and made everything. In the first project, they made everything much faster, and they also helped to save a lot of memory because camera chips are getting bigger and bigger, and so memory consumption really becomes an issue at one point. They hired a professional programmer from the Netherlands, and he really did a perfect job, did awesome enhancements to PIVLab. And so that was one project from MathWorks that they sponsored. And another one was where they hired a programmer that restructured the whole code into smaller, I think it's called namespaces. I'm not an expert still in this, but it's called, I think, namespaces, where you split up all functions into smaller folders and make everything much easier to maintain. So this was another project that was done recently, and I think it helps a lot. The aim of this project was also that people that it's easier for people to contribute to PIVLab, because it's not, in the beginning, it was really one single M file containing everything or almost everything with, like, I think 15,000 lines of code or something. It was a nightmare for everyone else except me, because I liked it. If everything is just in one file, it's super easy to find stuff, I think. But now I discovered better ways to find stuff and to find the code sections. It's much better now. But at that time, I thought this would be a good idea to have everything in one file. And now it's split up into, I think, 300 files or something like this. And yeah, it's much easier to maintain now. And that was the second project. And now the third one, that's why I started to talk about these support projects for MathWorks. The third one, we are discussing that maybe MathWorks can help me to incorporate stereo PIV to PIVLab. So they are still thinking about it. They are looking for, of course, they have to find some money for this. And they are looking for companies that can support me. And that would, of course, be awesome. If we have this, then yeah, stereo PIV is a very nice tool. I think in many cases, many people won't have an advantage if they use stereo PIV, because it also makes the setup much more complex. You have to do a lot of calibration. You have to put 2 cameras in there. You have there are many things that you have to keep in mind if you align 2 cameras and then there's an interface between water and air, for example, then everything will be distorted. You have to add some Scheinflug adapters to your lenses so that the lenses are tilted with respect to the image sensor, so everything is still in focus. So there's a lot of extra things that you add for getting one more dimension, because you're still working in a plane. Now we get 3 velocity components, but you're still in a plane. So it's a lot of extra work and extra things that you have to think about. So for my daily work, I would probably still use 2D, 2C, so normal PIV. But I think for many research questions where you can afford the time to set up your experiments, I think there you can benefit from it. But in industrial use cases, I think it's difficult to benefit from 2D, 3C.
So you're touching on an interesting point here of how you decide what becomes a feature and what gets in. So you released the new version 3.0 and it was a major release, lots of important things. Can you maybe talk a little bit about the process of how do you decide what makes it into a new version, and how do you maintain and keep track of all the things that you want to do and prioritize them? So I'm curious of how that process looks like and how you think about it.
Yeah, I just have a list on my mobile phone where I put all my ideas into, or all my ideas related to PIVLab and things. Sometimes I have just an idea what could make it easier to do your PIV experiment. Where could you benefit from drawing masks automatically? How could you do that and stuff like this? And just put it on my list. And then sometimes if I'm traveling for work in the Deutsche Bahn, so in the railway, then yeah, you have a lot of time. Sometimes I'm traveling 8 hours. I have internet. I have a lot of time. I have people that bring coffee and a croissant. So it's the perfect place to work. No one distracting me. Put on my headphones and I have 8 hours of time where I can just do nothing else than just writing code. And that's where I always get out my phone, look at the ideas that I had, and then just implement them. And it's really, I have the full freedom of implementing whatever I want, right? Sometimes people ask for specific features, and if I have the impression that I would also benefit from it, then, and that's the case, and in many cases that is true, that I would also benefit from it, then I just, think about it and start implementing it. And and also in the latest release, I added a lot of automatic masking features, or just I redesigned the whole process of how you can mask images, how you can mask regions in your images. And that makes it much easier if you're working with objects, flow around objects that have a lot of reflections and shadows and stuff like that. Then now it's much easier to draw your masks. And that was because I needed it. I implemented it into this.
So maybe talking about the latest release 3.0. So what are the main features? So when you say masking, just so I understand, so I think of it as like a large image and you're interested in a specific region, so you block out everything else, right? So that's when you say masking, that's what you're doing. You're zoning on a region of interest, correct?
Yes, exactly. There are two things to constrain where you are doing your analysis. There's a region of interest where you just draw a window and say, this region is interesting me. And then inside this region, there can be objects that reflect and stuff like that. And that's where you draw a mask. Yeah. So region of interest is the positive. That's what you want to include.
Yeah.
And mask is the negative, what you want to exclude from your stuff. Yes.
And what other cool features have you put in 3.0 which are worth calling out? Or that you had a lot of fun implementing, or
Yes.
did not have a lot of fun implementing?
Quite a long time. And also because usually when I implement a new idea, I want to get this out to the people, right? I say, this was so cool. People have to see it, right? But in this case, because I changed quite a lot of things. I think I took half a year or so until from the day that I started working on features, implemented a lot of new features, changed stuff, and then I released it. So it really, it took quite a long time. So the most important thing in version 3 is that I redid all the graphic display, how images are displayed, how like velocity maps and vectors are displayed. I changed this, and it required a lot of restructuring in the code. For example, to enable transparency, that you can select how transparent is your velocity map overlay onto your image. And that was a little bit difficult in MATLAB to get several images displayed on top of one another without taking too much time, because rendering also takes a lot of time then it's a lot of displaying issues that people complained about before. It's now exporting graphics from PIVLab now they look much better, and it's much more straightforward how you do it and how the result will look like. The result will always look like what is displayed on your screen. That was not the case before. Then I also spent some time to make it fully compatible with MATLAB Online, so with the browser-based version of MATLAB. There were some little issues because MATLAB Online is based on a completely different programming environment, I think, than the regular MATLAB. So it required some changes. And then I think the nicest addition were really these new mask generators. So a new way of drawing masks. I'm now using the region of interest tool from MATLAB, where you can edit the masks all the time, and they stay editable all the time. So you can tweak them as you like. And you can also have PIVLab generate masks automatically. So that means that if you have a bright reflections, you can just set some numbers, some median filtering, low passing, how is it called? Image open, image close, stuff like this. And then you can automatically mask regions in images. And that is actually not that easy, because we're almost always working with particle images. And from what I've learned so far, particle images are really a nightmare if you want to draw masks for these. It's really super hard to decide what is interesting regions of the image, what is interesting data, what is the reflection, what is the shadow, what is noise, because particle images, they are like going from 0 to 255 or whatever bitrate your camera has. So it's super difficult for automatic tools to mask this automatically. So if someone listened to this podcast and has an idea how to do this, because there's some space left, right? There, I have some simple mask generators, but there could be much better mask generators still. But everything is prepared to be implemented. So if someone has good ideas how to do automatic masking in PIV, then please let me know, or even better, just contribute something to PIVLab on GitHub.
So we will definitely add the links to that, to the projects on GitHub. But maybe just to understand, so your call to action is you're looking for more contributors, but do you have a few things that you would really like? So you could just call that one, but do you have a laundry list of things on your phone that you would say, hey, I need to do, I don't know, better documentation, translation, video. If someone would like to contribute, what are the things that you would like them to contribute on? Because I think that's often the case. Sometimes people want to contribute and it's orthogonal to where you want to go with the initial project, and that can be time consuming. So can you maybe walk me through some of the directions that you would love to take PIVLab on and you would love help with?
Yeah, I think I'm open to any kind of contribution, right? It can be documentation, whatever, but this is for many people, I think, not that interesting. So it can be new features, it can be advanced PIV technologies, it can be I really everything that sort of pushes the performance of PIVLab further. It can be memory optimizations still, speed optimizations, or new features, or no new pre-processing features, no new post-processing features. There's 3. Everything is open, I would say.
And would you like to comment on some of the things that you're working on that will be coming out in a 3.1 or a 4.0, or are they still in the planning phase?
Yeah, many things are still in the planning phase, but I think what I would really like to do is this stereo PIV feature. That is the next big step, I would say. It's really a big step because it requires a lot of changes. But that would be really nice, I think, if we have this in PIVLab.
And maybe just also to understand, so you say you've got these cameras, right? So how much data are you actually pulling and what is the resolution? Are these very specific cameras? Or are we talking like I just use my mobile phone and I put it on a stand and that's good enough?
No.
I'm assuming there's a bit more to it than just that.
Yeah, the cameras that we use, they are cameras developed specifically for PIV. These are called double shutter cameras. So they are capable of taking 2 images with 1 microsecond delay between the exposures. So these are very special, but also very expensive, but also very nice. So we have these cameras that we use often, and they have something like 25 megapixels. And the camera that I prefer has then only a frame rate of, I think, 2 hertz or 10 hertz. So it's a very low repetition rate, but with it's always 2 images. 2 images with a very small temporal separation. Then we also have industrial cameras, like regular industrial cameras, but it's a bit difficult always to find suitable cameras because you have to test them. You have to find out this interframe spacing, like how much time does it take for this specific camera when one exposure ended until it can capture the next exposure. And that is something that is not mentioned in the data sheets, unfortunately. You will actually have to order every camera that you think might be interesting and then put it on the oscilloscope, test everything. Then you find the timing and also some delays between when is the trigger coming in, when is the camera actually exposing. So there are a lot of things that you have to find out before you can include such a camera in PIVLab. And yeah, we have done that for some cameras, but not for many, of course. And then there are also very nice high-speed cameras. These are also industrial cameras. But the cameras I was talking about before, they have a normal USB 3 interface, right? And then there are other high-speed cameras that have a coax-press interface, which is pretty fast. And they, for example, my preferred camera from the high-speed cameras has 2 megapixels resolution and can capture, I think, at 2,200 frames per second. So that is relatively fast. And also the interframe time, which is super important for PIV, is like only 10 microseconds. So the delay from one image to the other. And this is very nice, but you can imagine if you're taking like 2 megapixels at 2,000 frames per second, and of course the image data is uncompressed, then you need, this camera captures to RAM, so you need a lot of RAM in a computer. And then you need a very fast hard disk, or not hard disk, but SSD, because otherwise it just takes ages until your cameras are transferred from RAM to your hard disk camera. So these are not very special, but you have to check every camera that seems to have some potential. You have to get the camera, check the camera, then find out all the timings, include all the timings that you find out into your synchronization software or the firmware of the synchronizer. And then we can sell this camera as a bundle with our lasers and synchronizers.
This is a great place to stop this episode. I hope it triggered your curiosity in some shape or form of how MATLAB, Python, or Julia are actually used in the real world. If you did find it interesting, just subscribe in your favorite podcast player. And while you're at it, write a review, as this will help the podcast going strong. In addition to that, don't be shy, share it with a couple of friends, as who knows, one of them might be a future guest on Inspiring Computing. Thank you.